So I'm going to start the new chapter, transistors. Transistors. Okay. Now just like how you had diode, in diode you had got one P and one N with non-rectifying electrodes. This was the PN junction diode. Correct? Now in transistor, what is, see, now this is what is technology. You can have a N layer sandwiched between two P layers with 3 electrodes, non-rectifying electrodes. Or you can have one P layer with 2 N layers, or a P layer is sandwiched between 2 N layers. So this is called PNP transistor and this is called NPN transistor. Clear? Hello? This is the first part. Now this one, see, now either this or this. The center layer, either this or this, it is called base. Right? Sorry, base. And this one is called collector. And this one is called emitter. Okay, so it is emitter, base, collector. Clear? Hello? This is how it looks. Now here you see the base layer. The base layer is thin. This is the base layer. The base layer is thin. Okay, this is thin. And then the collector region is large. And the emitter region is medium. I mean the size. I'm talking about the size. You have your PU textbook there? NCERT, anybody there?
No.
Open the textbook. Aram se. I want to correlate with the textbook. Please open the textbook.
Yes.
So is this what I have written correct there? The base is thin, the collector is large, and the size of the emitter is medium. Have they written like that? That is one part. Second part is you can find in the textbook that this is lightly doped. And this is moderately doped. And this is heavily doped. Please find these details are there.
Where will this be mentioned, sir?
I don't know. See, I told all of you read and come. So you don't read and come.
Transistor, they have started with the NPN and PNP transistors as 3 doped regions, forming into PN junctions between them.
Okay.
Emitter is moderately sized and
listen. See here. Emitter, it is the leftmost part. That is when you write like this. See, it is highly doped and medium in size. Got it? Base, middle part. Okay, it is lightly doped and very thin in size. Collector, it is large size and moderately doped. Correct? So that is precisely what I have written. Right? That is precisely what I have written. So size and this. So you can see there are P and P, but when they make P and P, these are the things to be considered. So size wise, this is medium, this is large, and this is thin. Size wise. And doping wise, this is heavily doped, this is moderately doped, and this is lightly doped. This is very important. Correct?
Yes, sir.
Okay, fine. So this is the first thing. Okay. Now stage by stage we will understand this. Stage by stage we will understand this. Okay. Okay. Now on the. So now you see, I am drawing the emitter. Emitter. So you like to consider the N type of emitter because it can be NPN or PN. N type of emitter with what? P type of base. Got it? Hello?
Yes.
So when this junction is formed, see, I am showing the electrode here, electrode here. When the junction is formed, what happens?
Some depletion region.
Now you see, this is heavily doped. This is lightly doped. So, okay, heavily doped, lightly doped. Depletion layer region is formed. Since this is heavily doped, this side the depletion layer is small, this side the depletion layer is large. Correct?
Yes, correct.
These are all very important to understand transistor. This side the depletion layer is large, this side it is small. Okay? You have to understand. Of course, this is the junction. First thing. Right. So therefore, the depletion layer is formed just like a normal PN diode only. It is just like a normal period. But you must know that this is the difference. Okay? Hello? Are you with me?
Yes, sir.
Good. Aram se learn. Now, if I forward bias this, then what happens?
Will start decreasing and.
So it just behave like a normal diode. Correct? No? Now, what is important here is, you see here, what is important here? Now look at the concentration gradient here and here. The concentration of the holes and the concentration of the free electrons. I told this is heavily doped. This is lightly doped. Since it is heavily doped, the concentration here is very large, the concentration here is comparatively less. Correct? So when you forward bias this, the majority charges. What are the majority charges? The electrons. So this becomes what? Electron current. Okay, and the holes are traveling like this. Correct? The holes are traveling like this. So if you take the conventional current, the conventional current will be in this direction because the electrons are moving like this. So the conventional electron current will be in this direction and the whole current will be in this direction. So totally the conventional current will be from what? From P to N or from base to emitter. Correct? Hello? I have written wrong here. You are also I think it was a good. Correct? So the conventional current will flow in this direction. Correct?
Yes.
But now you see. So if I say this is the conventional current, I will have IE plus IH. Correct?
Yes.
But now you see. Now since this is lightly doped and this is heavily doped, IH will be less than IE. Agree?
Yes.
And since it is lightly doped and this is heavily doped, for all practical purposes, you can take the current is only electron current.
Yes.
You understand? This is important thing. See, if they are equally doped, then IE is equal to IH. Otherwise, these two will be different. And in this case, it is made like this. That is, the conventional current when you have forward bias state will predominantly be that of the electrons or whatever is the emitter. So, and now here it is electrons. Okay. And whatever current is coming out of this node, we call it as emitter current. and whatever current is going to come out of, see, now listen here very carefully. It is going to come, we will call it as base current. See, here please understand, the convention is, we will always show the current in this direction, or you have to show it like this, the current entering. One of the things you should say, either entering or either it is leaving. Hello, are you with me? So, depending upon your textbook, you take it, depending upon a textbook, but what is important is the current that is coming out of this, the current coming out of this or entering here. One of the conventions is used. Current coming out, this is called emitter current and this is called base current. Clear?
Sir, that base current is coming out of this or entering this?
See, now if I say, if I now say here, please understand this. Now understand this very carefully. Now if I say the base current is 1 milliamp. The base current is 1 milliamp. And the convention I have used is, if it is coming out of it, I will write IV as the current that is coming out of this. IE is the current that is coming out of this. And this is 1 milliampere, and supposing this is 10 milliamperes. Then what will I write? I will write IV is equal to minus 1 milliampere. And IE is equal to plus 10 milliamperes. Convention, man, in optics and all we have used now. That's what I write. Okay, fine. So the current in the emitter is predominantly that of electron current. That is very important. So the whole current is negligible. Correct?
Yes, sir.
Okay. I hope all of you are with me in the class. Okay. It is very interesting, aram se learn. Somebody, I promised I will stop the class at 9 o'clock. I am continuing. 5 minutes I will continue. Oh, sorry. So this is the first thing that I wanted to teach you. Okay. Now you see. So that means now when you have a transistor like this, okay, and when you forward bias this, what is the time? It is 9:20. What is the time? Hello? 9:10. No? And I'll take another 10 minutes. Please excuse me, because I don't want to limit at this stage. So when I forward bias this, that is, I am using NPN transistor, and I am going to forward bias this. So then the emitter current. So here what I see is lot of electrons. See here, I am showing you. Lot of electrons are crossing here. Okay, electrons are crossing here, and negligible holes are crossing here. Got it? Because the doping is different. Hello, that's what I have explained. Hello. So therefore, you see, if this hole was equal to electron, then lot of recombination would have taken place. Understood? Now, hole current is negligible. So therefore, the idea here is there is very less recombination that is taking place, and you are able to push a lot of electrons from N to P when you have forward bias. Got it?
Yes, sir.
Yes.
Understand this carefully. Now you see. So this junction is called what? Emitter base junction. This junction is called emitter base junction, or sometimes also called base emitter junction. And this is called emitter base, and this is collector. So this junction is called collector base junction or base collector junction. Got it? Hello?
Yes.
Now, what I am going to do now here is, I am going to connect another battery like this. So I will call this voltage as VBB. I will call this as this. I am giving some name to this. Now don't ask me why you give BB and CC and all. Please. Okay. So what type of biasing I am doing here? See, negative plate is connected to N and positive plate is connected to P. So this junction is reverse biased and this junction is forward biased. Got it?
That is also forward.
This is also forward biased. This is also forward biased. Got it? Thank you. Now is it reverse biased?
Yes.
Thank you. This is reverse biased. Now you see some very interesting thing happens. So this junction is reverse biased. Hello? Hello?
Yes.
Now in diodes you have learned what will the reverse bias do in a normal diode? In a normal diode that we have just discussed. In a normal diode which is reverse biased, what will it do? What will the reverse bias do?
Try to increase the depletion there, sir.
Okay.
And you try to oppose the depletion there.
Okay. Anything else? Come on, correct.
It will act like open circuit. It will act like open circuits.
ಎಲ್ಲಿಂದ ತಗೊಂಡೋಗ್ಬಿಡ್ತೀವಿ ಗಾಡಿನ ಈಗ ಇಲ್ಲೇ ಓಪನ್ ಸರ್ಕ್ಯೂಟ್ ಮಾತಾಡೋದಿಲ್ಲ ಸ್ವಿಚ್ ಮಾತಾಡೋದಿಲ್ಲ ವಿ ಆರ್ ಸೀಯಿಂಗ್ ದ ಟ್ರಾನ್ಸಿಸ್ಟರ್ ಸಿ ನೌ ವೆನ್ ಯು ರಿವರ್ಸ್ ಬಯಾಸ್ ಇಟ್ ಫಾರ್ ಮೈನಾರಿಟಿ ಚಾರ್ಜಸ್ ಇಟ್ ವಿಲ್ ಬಿ ಲೈಕ್ ಎ ಫಾರ್ವರ್ಡ್ ಬಯಾಸ್ got it now? See, for electrons here and holes here, this voltage is, see, electrons here, this is negative. So these electrons, these minority charges will gain energy and these holes will gain energy too. Got it? That means the minority charges in this region and the minority charges in this region now will get more energies to cross the junction. Agreed? Now see, the electrons from the N have entered P. So the electrons here which have entered from here are what? Are minority charges.
Yes.
Minority charges in majority region. Got it?
Yes.
Correct now? Hello? So now this reverse bias, which one? This reverse bias. What will it do? It will now energize these electrons which have come here from here to move here.
Yes.
See, this has emitted the electrons. Emitted means it has emitted the electrons into the base region. Okay, and this reverse bias, what it will do? This will say, oh, Mr. Electrons are coming, welcome. They will start welcoming them this way. Got it?
Yes, sir.
Okay, yes. Now, what you have to understand is, say now here, some X amount of electrons are coming. Out of X only Y will come here. Only Y will come here, and X minus Y will go here. Got it?
Yes, sir.
So this will be X minus Y, and here what will come? Y, and so Y, and here again what will come here? X. Understood?
Yes.
Completed. So now here you see it's very important. What is important? Here you see the electrons that have come to base region. They have got some energy, and because of this reverse bias, they will get more energy to cross this junction, though it is reverse bias, and it will reach this point, or it will be collected by the collector, and this current is called collector current. Okay, and this is called emitter current, and this is called base current. So I will write like this. Emitter current will be equal to base current plus collector current. Correct? I am writing like this. Emitter current will be equal to base current plus collector current. Okay? I am showing the directions like this. Is that okay?
Yes.
Fine. Now, here are some things that you have to understand. So, this base current will be what? A part of the emitter current will flow to base current. A part of this will flow to the base. Okay, not all the current, some part of it will come to base, some others will go to the current. Okay, now understand this very carefully. Now this junction is forward biased, right?
Yes, sir.
So for the electrons to cross from here to here, it has to encounter some resistance. The electrons to cross from here to here, it has to encounter some resistance, right?
Yes, sir.
So that resistance we have called it as RF, forward resistance, correct?
Yes, sir.
Yes, sir. Now answer very carefully. For these very electrons to go from this region to this region, it also has to encounter some resistance.
Yes,
What is this resistance? RR, reverse, isn't it? Now you know very well that RR is very much greater than RF. Correct?
yes, sir. Yes, sir.
Okay, now understand this very carefully. So here you see, by slightly varying this VBB, we are able to vary this. We are able to vary this current. By slightly varying this, we are able to slightly vary this current. Correct?
Yes.
That is, you see, I can see now here the variation. See, if I vary this by delta V, this current is varied by delta I. So I will get delta I variation corresponding to delta V variation. This delta V variation corresponds to this. Okay. Now, majority of this delta I current will go to the collector. Correct? I mean, most of the delta I will travel to the collector region. Correct? Some will only travel to the base region. Why?
If it experiences a large resistance over there, why we should?
That is the beauty. That is what is transfer of resistance. I'll tell you, don't worry. I'll tell you. See here, did you understand? A lot of this majority, that is a large percentage of this current will travel to the collector. Appreciate it?
Okay, sir.
Okay. Now you see. Now all of you observe this.
So, but why not? Why don't?
Because this is reverse biased. See, that is what I explained initially. See, this is reverse biased. This VCC is larger than VBB. So there is reverse bias. So this is acting like a sucker.
This is still said that is like in microamperes, that is in milliamperes.
Pardon?
That current is in microamperes, no? So large cut will come there.
See, now what you have to listen here. First starting I told, say some 100 electrons will come here in a small interval of time. Out of 100 electrons, 10 will come here and 90 will go here. Agreed?
Why, sir?
Why? Because here this is, see what did I tell you? This reverse bias, this reverse bias is like forward bias for the binary charges.
Yes, sir. Yes, sir.
So it is going to suck, man.
Okay, sir.
See, now assume that I have got 100 marbles in my hand, 100 marbles. Okay. Now 100 marbles I throw. What will happen? 100 marbles I throw. What happens? All the 100 marbles will fall down. Correct now?
Yes, sir.
Now assume that I have got a strong sucker there. That is, it will suck the marble. Some very strong, force is there. So if I throw 100 marbles here, the strong force will suck 90 of them.
Okay, sir.
And 10 will escape and fall down. Got it?
Yes, sir.
So that is precisely what this reverse bias will do.
Okay.
Okay. Now you see, now just understand. Okay, I have got a resistor here. Say this is 10 ohms, and I have got a resistor here which is 1000 ohms. I have got a resistor here which is 1000 ohms. Got it? Okay. Now I want the current in this resistor to change by the current in this. I want to change by 1 milliampere. And here I want this current also to change by 1 milliampere. I want the current also to change by 1 milliampere. Okay. So now you see here, if I want to change 1 milliampere current here, then by how much should I change this voltage? So this voltage, how much I should change? Delta I into 10. That is 10 times delta I. That much voltage if I change here, then 1 milliampere will change here. Got it? But for me to do that here, what is this voltage change that I have to do here? Here delta V will be equal to 1 milliampere. Okay? So that is 10 into 1 milliampere. What did I say? 10 into 1 milliampere. So this much voltage I have to change. Here, what is it? Here 1 milliampere into 1000 volts. Correct? So I have to, if I connect a voltage source here of which can change by 1000 into 1, that is delta V should be 1000 times, and here delta V should only be 10 times. Correct?
Yes, sir.
So what I am trying to tell you, I will only change this voltage. Now listen here very carefully. I will only change this voltage with this example. I will only change this voltage by delta V. Okay, and how much will the current change here?
It will increase more.
Now listen here. I have changed the voltage by delta V here, and there is a corresponding change in here. Supposing for delta V this current change is 1 milliampere. Okay, and this 1 milliampere is flowing through, assume 10 ohms. This resistance is 10 ohms. The resistance here is 10 ohms.
Yes, yes.
But the resistance here is 1000 ohms. Correct?
Yes.
Now, by changing here by delta V, I can easily push 1 milliampere here. Out of 1 milliampere, 0.9 milliamperes will travel here. That means by changing this by delta V, I am able to send 0.9 milliamperes of current into the high resistance region. See, if in this case, if I want to send the same 1 milliampere, I have to increase this voltage by 1000 times. But here you see in the transistor action, I am increasing this by delta V, but still it is able to transfer the current into the high resistance region with only a small change in the voltage.
Okay.
So you are able to push the current in a high resistance region with very little effort.
Yes.
With very little effort. Now please understand this very carefully. You know Pascal's law?
Yes.
This side, a small boy will push the lever. A car of nearly 500 kgs will rise up. Got it?
Yes.
So what has happened here? Small effort, large change. So there is force multiplication here. The force has got amplified. Got it? Pascal's law, man.
Yes, sir.
And here what has happened here? Similarly, small force, corresponding to the small force, there is change in the current here. Say, assume that this current change is 1 milliampere due to small effort that you have put. Now, out of this 1 milliampere, 0.9 milliamperes is coming here, but across a large resistance. So, you can make a current to flow, you are only putting effort to make the current flow in a small resistor. You are only making effort to push a current in a small resistor, but the mechanism is such that the majority of the current that is flowing in the small resistor, it will automatically flow into the larger resistance. If you are directly wanted 1 milliampere to flow in larger resistance, you have to put more effort. That is, if you want to lift Maruti car with your own hand, then you have to be a Tarzan. But here, a small boy can do something like this, use Pascal's law and do what a Tarzan can do. That is precisely what it is. Transistor here means you are transferring the current. You are making the current flow in a small resistance region to get transferred into another circuit where it is high resistance. That is why the name transistor, transfer of resistor. Okay? You will understand this much better. First class only you will not understand. This is basically what happens. Okay. Now, yes please. You have any question? Ask.
So when we increase the current, sir, still it can flow through everything.
It will flow, but small current will. I'll explain this. Correct. I will now give you one more example. You will understand. You will understand. Arama, be calm and cool.
Yes.